Okay guys, in this video we are going to talk about the kinetics of reversible reactions. So here's an example. We have a generic reversible reaction that's first order in each direction. So the forward direction is first order with this rate constant, and the reverse reaction is first order as well with a different rate constant. So in general these are two different numbers. Well, let's take a look at what would be the change in the concentration of species A with respect to time. Well, the forward direction would tend to decrease the concentration of A. Okay? And so since it's first order in the forward direction, we'll write minus, because it decreases the concentration of A, times the rate constant, and since it's first order, it'll be just times the concentration of species A. Okay? So this is equivalent to saying that the forward direction is first order. However, we also have the reverse reaction. So the backwards reaction or the reverse reaction, that would tend to increase the concentration of species A. And so that's why we have a plus sign here, because that would tend to make the concentration of A increase. It's also first order in the reverse direction, and so it's just the reverse rate constant, K prime, times the concentration of the product species B. And you can write a similar equation, but just of opposite sign here, for how does species A change with respect to time. Well, you can take those two differential equations and then integrate them together, and that leads to this integrated rate law that we have right here. And so you see that it does have this exponential component to it, but it's quite a bit more complicated than just the ordinary first order reaction that we had before due to the presence of all of these constants. And then here would be just due to stoichiometry, this would be the expression for species B's concentration. I think, yeah, and it just depends upon, what starting conditions you have. It looks to me like what we've started with would be the initial concentration of A would have some value, but then the concentration of B would be 0 initially. And so those initial conditions make a difference for what the form of the integrated rate law would be. And so we started off I believe this is for the case where the initial concentration of B is 0 at time t equals 0. If you had a different initial concentration of species B, then you would have different looking equations. They'd be more complicated. So by definition, when you have a reversible reaction, the long time limit is the equilibrium limit. So if you wait long enough, eventually this reaction will come to equilibrium. If you take the integrated rate law here and substitute in t equals infinity, e to the minus infinity gives you 0, so this numerator cancels out, and it leaves you with this kr prime over the sum of the two rate constants times the initial concentration of A0, so that's the equilibrium concentration of species A. And then if you just substitute in this expression here and simplify, this is the expression you get for the equilibrium concentration of species B. Okay, you'll notice that the denominator is the same in both, but the numerators are different. When you have a reversible reaction that reaches equilibrium, we often call it a dynamic equilibrium. What that means is that even though the reaction has reached equilibrium here and there's no net change in the concentration of species A or B, that doesn't mean that reaction A doesn't continue to happen and reaction B doesn't continue to happen. Indeed, reactants A are constantly being converted into reaction B, into products B, and B is constantly being converted back into species A. However, they do so, these two reactions occur with the same rate. Therefore, there's no net change in the overall macroscopic concentration of species A or B. And so that's what's written here. The forward rate equals the backward rate when the concentrations have reached equilibrium. And you can, from this relationship, from this kinetic relationship, you can then extract the thermodynamic equilibrium constant by, by taking the equilibrium concentration of B divided by the equilibrium concentration of A, and you see that the thermodynamic equilibrium constant is defined in terms of the rate constants, the forward and the backward rate constant. And if you had multiple equilibria, so suppose that you had reactants 1 in equilibrium with intermediates, I don't know, we'll just call this 0, call that 1, 2, etc., just going on, and then ultimately arriving at some products. The overall rate constant for the equilibrium between the reactants and products would involve the rate constants for each step. Here's an example of taking this, taking these two integrated rate laws, okay, and plotting them versus this compound time unit given here. And initially we start off with no product and all reactant, and what happens? You see that the reactant concentration decreases and the product concentration increases. Eventually, however, what you find is that the curves flatten out. They become constant at a long enough time, and that's where we say that the reaction has reached equilibrium when the concentrations no longer change anymore. The forward rate equals the backward rate, and we're at equilibrium. In this problem here, they give us, they're asking us to consider a dimerization reaction. And they give us the two rate constants, so they give us the forward rate constant and the reverse rate constant, and they're asking us to calculate the equilibrium constant. So we would say that the forward rate, K1, A squared, at equilibrium, second order in the forward direction. That's what they tell us. Notice it says second order. And then it's first order in the reverse direction. The forward rate equals the reverse rate. And then to build the equilibrium constant, what we would do is we would want to take A2 equilibrium divided by the standard concentration, and we would do like so. The purpose of that is to get a unitless equilibrium constant. Anyway, we'll end up having that, and then we get this ratio from this kinetic expression here, which is going to be K1 over K minus 1 times C0 to get the units correct. And so we would just plug in those numbers, and C0 is equal to 1 mole per liter. That would cancel out the units, so that we would get a unitless rate constant. All right, the next subtopic here discusses how to measure kinetics for reversible reactions. In particular, when the reactions are fast. So when it's a fast equilibrium reaction, like an acid-base reaction or something like that, the reaction occurs so quickly you can't really study the concentration versus time dynamics with any type of accuracy and precision. Fortunately, though, there's another approach that you can use or the general term is called relaxation methods. And so if the initial rate method is not applicable to your reversible reaction, you can use a relaxation method where you perturb the equilibrium mixture somehow, and you monitor its relaxation back to the new equilibrium. One common approach is to do a temperature jump that will have the effect of altering the rate constants and the equilibrium constant and the extent of reaction. And so what you can do is, I don't know, you can zap your solution with electricity to change the temperature, or you can shoot it with a laser beam. That's going to perturb the solution very quickly, and what will happen is that the solution will relax down to a new equilibrium. So let's, if you had some T-jump method, okay, we're looking at first order kinetics both in the forward and reverse direction. You know, when you increase the temperature, you're going to increase these rate constants, which depending upon which one increases by more and so on, which actually connects back to thermodynamics. That's going to determine whether the equilibrium constant gets larger or smaller. Either way, you're going to wind up with a time-dependent concentration for your reactant product that's going to depend upon this response function, xt, and it's going to have equal but opposite effects on the reactants and products. So notice here it's the original equilibrium plus xt, where xt is the relaxation function, and then for B it's the equilibrium concentration minus that. And here's the generic format for these types of perturbations. So there's some maximum value of the perturbation, and then this is the decay function. Okay, so it starts off at 0, you know, when time t equals 0. That's when you perturb the system. Okay, you'll have e to the 0, so it's the maximum displacement from equilibrium, and then as time goes on, this function gets you'll get e to the minus infinity, which is 0, so the perturbation function will decay exponentially. By measuring the time scale for this relaxation function and knowledge of the equilibrium constant, you can determine what the forward and reverse rate constants are. So by monitoring the relaxation back to equilibrium and having previously measured the equilibrium constant, you can determine the two rate constants independently. That is, K is equal to Kr divided by Kr prime. So you have one equation and two unknowns. And then when you determine tau, that gives you a second equation for determining the two rate constants. And the results, like whether you shift to the reactants or the products by doing the T-jump method, depends upon the enthalpy of the reaction. Right? We looked at this previously when we discussed Le Chatelier's principle. If you've got an endothermic reaction, so you've got your heat temperature term over there, and you jump the temperature, it's going to shift the reaction to the products to get to the new equilibrium. So you monitor now the kinetics of that process. Conversely, if you had a exothermic reaction, so your heat temperature term is, you can think of it conceptually on the product side, if you increase the temperature, that's going to push you back to the reactant side. Okay, so it just depends upon the thermodynamics of the reaction, which way it's going to shift. Either way, it is going to shift. And then so you'll do things like, okay, you're sitting at equilibrium at your initial temperature, then you zap it with a laser beam or something like that. That increases the temperature of your sample very quickly, and then you monitor the sample's return to the new equilibrium. And from this exponential curve, you need to do a fit to get the value of tau. Combining that with K allows you to determine the two rate constants. So that's the idea of this method. And so I'm going to go ahead and keep this one pretty short, so I'll just stop the video right here, and we'll talk about the temperature dependence of kinetic rate constants in the next video.